Okay, for questions 7 and 8, we're talking about specific heat capacity. Basically, these questions are going to be sent around, how much energy is required to change the temperature of a certain amount of something. So like water, and I chose the other one, cement, okay? So if you're trying to change the temperature of a certain amount of something, we're looking at specific heat capacity. The fundamental equation in solving these problems, Q equals mc delta T. Q is energy, m is mass, and I should say this is energy in joules. This mass, typically they'll give it to you in grams. It might be kilograms, depending. The specific heat capacity is going to be in joules per grams degrees Celsius. Might also be in maybe kilojoules per kilogram degrees Celsius. It just depends on how you might see it. The point I'm trying to make here is pay attention to your units because they have to match up at the end of the day. And temperature is either degrees Celsius or Kelvin. Doesn't matter which one because we care about the change in temperature, not the absolute temperature itself. Whether it's Celsius or Kelvin makes zero difference for this equation. If we're talking about some other things, it really does matter. But for this one, it doesn't. Okay, so let's just jump into the first one, number 7 here. We have how much energy is required. All right, so we have 4 different unknowns, variables here, potentially 5, because this can be broken into T final minus T initial. So all we got to do is write out our list, match them up. So the question says, how much energy? Well, I know that this is where my question mark goes. Is required to heat a glass containing, it says 48 grams of water. Well, that sounds like a mass. From 24 degrees Celsius to 82 degrees Celsius. Final minus initial. 82 degrees Celsius minus 24 degrees Celsius. And let's see here. It says specific heat capacity is 4.184. And that would be joules per grams degrees Celsius. All right, looks like we have all of our unknowns filled in except for one. That's great news, which means we can solve this problem. So we're going to fill them in. We have Q equals 48 grams times 4.184 joules per grams degrees Celsius times delta T, T final minus T initial, 82 degrees Celsius minus 24 degrees Celsius. And let's simplify it once here. Q equals, we'll say 48 grams, 4.184 joules per gram degrees Celsius. And I'm just going to solve that real quick. 82 minus 24. All right, that's 58 degrees Celsius. And just a quick note on the units here. I can see grams divided by grams, degrees Celsius divided by degrees Celsius. I'm left with joules, which makes sense because energy is measured in joules. All right, so Q equals, going to get 48 times 4.184 times 58 equals. All right, so now we have 11648 joules, and I'm going to say, okay, it's 1.16 times 10 to the, here's my decimal, 1, 2, 3, 4, times 10 to the 4th joules. There's my final answer. 1.16 times 10 to the 4th joules. All right, let's go ahead and do the next one here. All right, so number 8 is talking about concrete instead of water. So it will likely have a different specific heat. A specific heat is a property of a certain substance. So water has its own specific heat. Concrete, wood, anything else, any metal, any other liquid, they all have their own specific heat. So you'll have to be given that value unless that's what you're trying to calculate anyway. All right, so once again, we have Q, M, C, delta T, which equals T final minus T initial. So we're going to see, I don't remember what we're solving for here. So we have 445 kilograms. 445 kilograms. It says it starts at 25 degrees Celsius. So this is something. It says energy is lost. All right. So we have 1.958 times 10 to the 3rd kilojoules. It says energy is lost. We'll talk about that. Specific heat capacity is given in so we have 0.880 joules per gram degree Celsius. Okay. All right, so the question is, what is its final temperature? So T final is actually what we're solving for here. How do we know if the temperature will be higher or lower when we solve this thing? We would expect, if this is energy lost, then we know this is going to be negative. That's very important because without the correct direction, then we will get the wrong final temperature here, okay? All right, so let's go ahead and talk about maybe what we need to do before we can even get started here. I'm looking at these units, kilojoules, kilograms, degrees Celsius. That's fine. I need to convert one of these into either joules or kilojoules. Same thing with the grams, kilograms. I think what I'm going to do is end up converting the specific heat capacity because then instead of converting two separate things, I'm only converting one here. So what I will do is say, okay, I know for every 1,000 joules, I have 1 kilojoule. And here, for every 1,000 grams, I have 1 kilogram. Okay, what's 1,000 divided by 1,000? That equals 1. I can just cancel these out, except for the units will still be transferred fine. So we have 0.880 kilojoules per kilogram degree Celsius. Well, that was pretty lucky that worked out just fine. Okay, now we need to set up our problem. Let's see, I think what I'll do is I'll set it up over here, erase this, and then we'll work through the algebra. So I'm going to get negative 1.958 times 10 to the 3rd kilojoule equals 445 kilograms times 0.880 kilojoules per kilogram degrees Celsius times T final minus 25 degrees Celsius. Okay, so I'm going to erase this right here real quick and we'll work through the algebra. What do we have to do to solve this thing? Our goal is to isolate our T final. So the first thing I'm going to do is divide out these two elements here, okay? So I will get negative 1.958 times 10 to the 3rd kilojoules over the quantity of 445 kilograms times 0.880 kilojoules per kilogram degrees Celsius, and that equals T final minus 25, degrees Celsius. All right, so now I can just add 25 to this and we'll be good. So our final is going to be 25 degrees Celsius plus, well, actually, that is a negative, so minus 1.958 times 10 to the third kilojoules over quantity of 445 kilograms times 0.880 kilojoules per kilogram degrees Celsius equals T final. This is what calculators are for, so let's throw that in real quick. I'm just going to throw this in as I see it here. So I'm going to get 25 minus 1.958 times 10 to the third divided by 445 divided by 0.880 equals 20. So the final temperature is 20 degrees Celsius, and we have kilojoules divided by kilojoules, kilograms divided by kilograms, degrees Celsius, so this is per degree Celsius, reciprocal, and that is our final answer. All right, that is, again, how to solve this one. Ask for the final temperature given the other information. Cool. One more problem.